the functions that are approximate, then why do we need to look at anything that's, oh, wait, hold on. Sorry. Let's just move this. There we go. Yeah. So you might be wondering then, why do we need something that's different from that architecture? And there are a couple reasons why we turn to convolutional neural networks as something being more powerful than just run-of-the-mill fully connected networks. For one thing, if we consider the weights that we want to optimize, right? You might recall that the more weights a model has, the more dimensions its parameters sit in. If you look at in terms of optimizing parameters, and the more parameters you have to optimize, the more data you need, the more epochs you need to run, the more expensive it is to train it overall. So if you look at our images, right, for an image that's like pretty like pixelated, just 100 pixels by 100 pixels, even that, if you just connect it to a really, really tiny second layer, you're going to have to end up learning 60,000 weights for just that pair of layers alone. And that will like compound the more weights and layers that you add to your model. So this is already like a really, really big problem, which requires a lot of data in order to optimize. So that's one problem. Okay, there we go. So to solve this problem, we create the idea of a convolutional layer or filters. And so these filters are, sorry, let's go. There we go. Yeah. Is something back? Yeah.
Wait, so you need to press it again.
Oh, okay, I see. There we go. Okay. So a CNN then is a type of neural network that we use to solve this problem, where the model learns filters that it then runs over images to extract feature maps. And then you apply those filters, further filters over those feature maps to get higher level feature maps, and so on and so forth, until you finally get a smaller feature map that you can then flatten out and put into a fully connected layer. And because these filters that you have to learn are on the order of 3 by 3 or 5 by 5 or something like that, it's a lot less to learn in terms of optimizing parameters than it would be to have just like a giant fully connected layer connect to like every single pixel of your original image. Another nice thing that you get with these feature maps is that if you haven't some sort of image that you start with, and then you sort of like move it around in the image, that's going to like lead to pretty different results from a fully connected layer perspective because all of the pixels change. But if you run feature maps over it, you're more likely to extract those features that you're looking for. And that makes it resistant to this idea of translating your image over the photo or over the pixels. And that makes it a better model overall because it's less resistant to these spurious kinds of noise. Okay. So running really quickly through the parts of a CNN, we have, well, really two main parts, the convolutional part and the fully connected layer. We've already gone over the fully connected layer part, and now we'll focus more on the convolutional part, which follows the format of convolutional layer, pooling layer, convolutional layer, pooling layer, all the way until you go to a fully connected layer. Okay. So if we talk briefly about convolutions, I think we can skip the continuous case. But if we look at sort of the more discrete case, which is more applicable to our concerns, the idea of a convolution is basically just you take this filter, which is denoted by this square right here, and you just take the dot product of the values in the square with the parts of the image that the square is overlapping with. And you just keep running the square over as it's doing right here. And you just keep filling in the image, you keep filling the numbers into this grid. And so if this is your input image, let me just wait for that to run. Just give that one moment to, yeah, there we go. So this 9 would then be one of the pixels in your feature map. And as you can see, it's calculating all the values that need to go into this feature map. And so you start with this input image, you end up with this feature map, and then you can run further filters over this feature map that you would learn. And then that's how you'd get higher level feature maps and so on and so forth. And so these 9 values are the things that you would need to learn. These would be your parameters. Okay. So the convolutional layer then is this learnable filter that's running over our model. And when we talk about this filter itself, there are a couple things that we need to learn about it, that we set as hyperparameters for it, rather. One of the things we'll set is the height of the filter. So in that previous case, it had a height of 3 pixels. We'll set a width for it. In this case, again, it was 3 pixels. So it was a 3x3 filter. And the number of channels, which tells you how many channels from your input image would be occupied by your filter. So if you have a traditional RGB image, right, that's going to have 3 channels. So you might have a filter with 3 channels as well that will take into account all of those things. Another thing you have to think about when you're designing your filters as a hyperparameter is the stride. So the stride tells you how many pixels you're going to skip as you keep moving your filter. Because if you go back here, you can see that the square itself is moving, right, 1 pixel at a time. But that doesn't need to be the case. You can move multiple pixels at a time. You could move 2 pixels at a time and so on. And the more pixels you skip, the smaller your output feature map is going to be. There we go. So if you take into account all of these things, you end up with this idea of something that has some height, some width, and some number of channels, and it's moving over your image as dictated by a stride. Yes?
Like, why would you ever want to scale?
Well, because the idea is that we want to make our feature maps smaller so that when we finally unroll the final feature map, we can like plug it in. And also what we might find is that there are some details in our image that might not be super useful, right? Or you might double count them if you like move just 1 pixel at a time. It really depends on like what kind of model you're trying to construct. So you can like determine the stride like according to your own arbitrary choices.
So
And the notation for that.
the memory.
I guess not just the memory, but just from a learning perspective, right? We're trying to minimize the number of weights that we have to train. So the smaller our feature map is when we unroll it, the easier it is to learn.
That's the, we can apply like.
There we go. So with this stride, you might notice that like some parts of the filter like sort of go outside of the image, right? Which doesn't really make sense for like a lot of applications. So the way that we just address this issue is that we'll just like add a layer of padding around our image. So that way everything works out mathematically so that you end up always like overlapping with some part of the image instead of like being outside of the image and not knowing what to do. And so this padding is typically going to be just zeros. So you'll just add like a bunch of zeros like in a square fashion all around your image so that you end up with the appropriate padding relevant to a stride. Yes.
One thing that NumPy
So for how convolution works, it does have to be like starting from the left and going right, starting from the top and going down. And that's sort of analogous to this continuous case, where if you like look at this filter that's running over your function, you can see it's like going like smoothly from left to right. So it's the same logic there is why it does have to go according to that pattern.
So for instance, I had like 0, 1.
Okay.
2,
There we go.
3.
So once we've run the filter over our image and we've gotten a feature map, the next step is something called a pooling layer. We're going to take some cluster of pixels and then reduce them to 1 pixel, either by taking the maximum of those pixels or by taking the average of those pixels. Typically, we'll be using max pooling instead of average pooling. And you can see like the effects of the pooling here, where you have these like clusters of 4 pixels and you take the maximum of that cluster and you just like have that be the value for that cluster. And then you repeat that for this side, the bottom, yeah, and this part here. So you can see that again, we've reduced the size of it. And the goal here is to extract only the most relevant part of the feature map. So that way you can see that the 100, like that part is going to sort of dominate over the rest of it. So that way, if we just isolate that, we'll get like a lot of the information for that region of the region without needing to necessarily account for every single part of it. Yes?
So, what's the rate? It'll sum up like every corresponding like.
Okay.
So if you.
Oh, wait, hold on. Let me just wait for this animation to go to the beginning.
Yeah. Down the call.
Okay, so we're taking the dot product of these values here in this filter with the values they overlap with in here.
So this is outputs.
The values in here are your input image. The values here are your filter. So when you're taking the dot product, you're taking the dot product with the filter and the part of the image it overlaps with.
Okay.
So basically you do that dot product, you run that over the image. Once you've done that, you'll end up with a feature map. You'll make the feature map a little bit sharper with a pooling layer, and you'll end up with some new array. And then you can run this through that same process again, run it through a convolutional layer, extract a higher level feature map, do max pooling on that. You end up with something else. Repeat, rinse and repeat, all the way until you end up with something that you feel is appropriately small. Then you unroll, then you sort of unroll that into a single one-dimensional array, plug it into a feed-forward neural network, and just like before, like we talked about last week, the rest of it is just like that. Okay, perfect. So this is math that you don't really have to worry about. This is just a way of determining what the dimensions of your output are going to be based on the width of your image, the width of your kernel, height of your image, height of your kernel, and the padding and the stride of your kernel. Based on all of these factors, you're going to end up with some sort of feature map that has some sort of dimension. And this is just a way of calculating what the dimension of your feature map is going to be for after you've gone through your convolutional layer. Where W output is the width of the output, H output is the height of the output, and D output is the number of channels that your convolved feature is going to have. And one thing to note is that when we're running our filter over our image, right, and we're getting this feature map, we don't have to just do that once. We can do that multiple times and get like multiple feature maps by running like some filter over our image. And then we can, from these multiple feature maps with like multiple channels, we can then apply the same process across the multiple channels as well. So we're not limited to just extracting one feature map from the image at one time. We can extract multiple feature maps and then combine those in subsequent convolutional layers. And hopefully that'll make a little bit more sense when you actually get into the CNN notebook. Okay, perfect. So this is sort of a visualization of why we prefer feature maps over just fully connected layers, which is the top layer here is a fully connected layer where you pass in the MNIST number 8 as an input. And you can see these are the features that the fully connected layer is looking for, right? It's looking for something that's kind of abstract, sort of smeared, not really human interpretable. But if you look at the bottom, what the feature map is looking for when you plug in 9 as an input, you can very clearly see that it's sort of spiking over parts of the 9 that are relevant to the actual classification. It's detecting these loops, it's detecting these lines. And if you look at these filters, you can see they're sort of responsive to like certain parts of the image. And that's how you can sort of like get a sense that the CNN is going to learn faster because it's learning these specific features that are more relevant to the calculation. Okay. So now we'll just like run through the CNN portion of the CFAR 10 notebook real quick. And again, when you actually like go to the CFAR 10 notebook in your group, you'll go through this in more detail. We'll just sort of give a high level overview here real quick.
So if I do
Okay.
This case, all shape will do is we'll define here the.
Okay. So to get started, first we're gonna import the libraries that we need. We're gonna switch to the GPU. That's just like standard across all ML programs. Then we're gonna get our data set, again, standard across all ML programs. And we're gonna make our train loader and test loader, again, standard across all ML programs.
Which stores two, right? And then each of those.
Okay.
two,
So we talked about this already. Well, you guys can talk about dropout in your notebook.
So.
Okay, there we go. So you can see that this is sort of like where the difference arises, is right here. So we add a convolutional layer right here, and we're gonna define it with some sort of predetermined, with some shape that we're gonna determine. Then we're gonna run that through an activation function, and then you can talk about batch normalization and dropout in your groups. But these are additional ways of sort of making sure that our model doesn't become too reliant on any one given feature being like extremely high.
Pretty good.
Then again, we have a second convolutional layer. Then we're gonna normalize the batch, sort of take the average over the batch. Then again, run it through an activation function, add a pooling layer right over here. And then again, this dropout rate is gonna sort of prevent our model from being too reliant on any one given neuron. And it's gonna do that by sort of zeroing out connections as it trains. Again, we'll go into much more detail on this in your when you go into your groups. So you can see that we've added these convolutional layers. Then we have our pooling layer right after. We have a convolutional layer. And then after this, once we've done that, through these three convolutional layers, we can just flatten it out and then attach it to a fully connected layer right over here. On the code. Command plus, yeah. Okay. Right. So hopefully you guys can see this a little bit better. Okay, yeah. Again, just to go through it real quick, I'll focus on the second convolutional layer specifically. We have our convolutional layer where we define like what the input shape and output shapes are going to be. Then we perform this thing called batch normalization. Then we use our activation function. And finally, we add a dropout layer where we zero out certain connections during the training process to prevent our model from being too reliant on any given neuron being like extremely active. Okay. So that's really it as far as like the implementation of convolutional neural networks goes. You just have to add the conv layers and the batch norm ReLU dropout layers and then pooling after that. That's really it. Okay. And then after that, instantiate your model, put your model onto the GPU, define your loss functions and your optimizers, and then you just plug that into the model for the training loop and you just run it. And then once the model trains, then of course you can analyze it the same way. So really the new part here, as far as CNNs goes, is just this section here, this initial section. Everything else, if you've gone through the MNIST notebook, should be relatively familiar. The only thing that should be different is this initial part with the convolutions and the pooling. Okay, and
all this will do.
This would be the kinds of images that you would be training with the CFR10 notebook. And you can see that after the model is done training, it's sort of able to analyze things more effectively.
2 on one line, 3 on another line, 4 on another.
Okay,
It's really
perfect.
It's really good.
So I think that should be it as far as the general presentation goes. We can start splitting off into groups now where, again, introduction to Python going over here, MNIST notebook people go over here, and then CFR10 notebook people would go over there. And yeah, I think we can start splitting off and then doing our own things. Does anyone have any questions before we do that?
Oh, yeah.
Okay, right. Let's get started then.